Think about the world around you. The bridges holding up highways, those huge buildings, car engines, even just the tools in your toolbox. So much of our modern world is built on materials that are, well, fundamentally just a mix of iron and carbon.
That's right.
But how can such a simple combination, be shaped into things as vastly different as, say, a soft bendable wire and a super hard cutting tool?
Yeah, it seems counterintuitive sometimes.
It all starts with understanding a map, a really critical map.
A roadmap for materials, you could say?
Exactly. So today, we're taking a deep dive into that very map. Our guide is a foundational text in material science, the book Material Science and Engineering, an introduction by Callister.
A classic.
Definitely. We'll be pulling key insights from Chapter 9, which lays out the principles of phase diagrams, and we're specifically drilling down into the section on the iron-carbon system.
Point.
Our mission, then, is to navigate this absolute crucial map, what's known as the iron-iron carbide, and sort of unlock the secrets behind the key phases and microstructures that give these iron alloys their incredible versatility.
And understanding this specific diagram isn't just academic, it's fundamental.
Yes.
Like you said, steels and cast irons are the backbone, really the primary structural materials in essentially every technologically advanced culture. This diagram is the core basis for predicting how they behave and, maybe more importantly, how we can engineer their properties, how we can tweak them.
For specific jobs, yeah.
Exactly. And we'll focus our deep dive on the iron-rich side of the diagram, looking at carbon content up to about 6.70 weight%. That particular composition is significant because it corresponds exactly to this compound called cementite.
Fe3C.
Okay, so let's unpack this map then. Looking at figure 9.24 in the source.
Yep, the main diagram.
We see the standard setup, right? Temperature running up the left side,
Yeah.
usually in both Celsius and Fahrenheit.
For convenience.
And then across the bottom, that's the composition axis, typically in weight% carbon, though sometimes you see atomic percent too.
Right. And let's start with pure iron itself. That's the far left vertical axis, 0% carbon.
Okay.
At room temperature, pure iron has a body-centered cubic, or BCC, crystal structure. We call this phase ferrite.
Alpha iron, got it.
Now, as you heat pure iron up, it does some pretty interesting things. It transforms. It shifts from that BCC structure to a face-centered cubic, or FCC, structure at 912 degrees C.
So it rearranges its atoms.
Precisely. And this FCC phase is called austenite, or gamma, and it's stable over quite a wide temperature range.
Okay.
If you keep heating it, keep pouring energy in, the austenite transforms back to a BCC structure, which we call delta ferrite, at 1394 C.
So it goes BCC, then FCC, then back to BCC.
Yeah, before it finally melts into liquid iron at 1538 C, or 2800 Fahrenheit. So pure iron itself is quite complex just on its own.
And just to clarify the composition scale again, even though we call it
Fe3C
diagram, treating cementite as a component. The horizontal axis is weight% carbon. So that's 6.70 weight% C on the far right. That represents 100% cementite.
Exactly right. Now, where carbon comes into play is that it fits into the little spaces between the iron atoms in these crystal lattices.
Oh, the gaps.
Yeah, it's what we call an interstitial impurity. And this is where the specific crystal structure of the iron, BCC or FCC, becomes critically important for how much carbon can actually dissolve.
Okay, how so?
Well, the solubility of carbon is extremely low in that room temperature BCC ferrite, really tiny. The maximum it can hold is just 0.022 weight%, and that's at a fairly high temperature, 727 C.
Wow, that's almost nothing.
It's practically negligible at room temp, and the reason is basically the size and shape of the interstitial sites, the gaps in the BCC structure. They're just not a good fit for carbon atoms. They're too small, awkwardly shaped. But contrast that with the FCC austenite phase. The maximum solubility of carbon in austenite is dramatically higher. It can hold up to 2.14 weight% at 1147 C.
Whoa, that's a huge difference.
It's roughly 100 times more carbon than ferrite can hold. The FCC structure has these larger octahedral interstitial sites that can accommodate carbon atoms much more easily. It causes less strain on the surrounding iron lattice.
So it's really just about the geometry. The arrangement of the iron atoms dictates how much carbon can physically squeeze in.
Precisely. And this difference in structure and therefore carbon content leads to very different properties.
Makes sense.
The
Alpha
ferrite, the BCC stuff, stable at room temperature. It's relatively soft, quite ductile, and it's magnetic below about 768 C. If you looked at it under a microscope, like in figure 9.25a,
Okay.
you'd see these distinct grains, sort of irregular polygons packed together.
All right. And austenite.
The austenite, the FCC phase, that's non-magnetic. It's also quite ductile, which is really important for forming and shaping steel when it's hot. Under a microscope, like figure 9.25b, austenite also shows grains, maybe slightly different shapes, often with annealing twins.
Okay.
That high-temperature ferrite, the other BCC phase, it's generally less technologically important because it only exists at very high temperatures, so we don't encounter it much in final products. Ferrite and austenite are the main players we deal with.
Got it. And then moving across the diagram, we hit cementite, ferrite. That vertical line at 6.70 weight percent carbon, it forms when you have more carbon than can dissolve in the iron phases, right?
Exactly. It forms when you exceed the solubility limit in either ferrite or austenite, and it can exist alongside both of them in those two-phase regions you mentioned.
How does it compare to ferrite and austenite?
Well, cementite is fundamentally different. It's not just iron with some carbon squeezed in, it's an intermetallic compound, a distinct chemical entity with a fixed ratio, 3 iron atoms to 1 carbon atom. And critically, property-wise, it is very hard and very brittle.
Ah, so that's where the hardness comes from in harder steels.
Largely, yes. The presence, amount, and distribution of cementite within the microstructure are what primarily gives steels their strength, but also influence their brittleness.
Okay.
Now, there's a slight technical point. Cementite is actually what we call metastable.
Metastable, meaning?
Meaning it's not the absolute lowest energy state under all conditions. Over, geological timescales, or if you held it at high temperatures, say 650, 700 degrees C, for a very, very long time. It can eventually decompose into no iron and pure carbon in the form of graphite.
Graphite, like pencil lead.
Essentially, yes. But, and this is the key point, at typical room temperatures and for basically all practical engineering timescales, this decomposition is incredibly slow. So slow it just doesn't happen.
So we can ignore it for most purposes.
Exactly. We treat cementite as if it were stable. That's why the
FEF-E3C
diagram is perfectly valid and useful for analyzing steels and cast irons in almost all real-world applications.
Right. And looking back at figure 9.24, you can clearly see those regions labeled with phase combinations.
Now, moving on from the individual phases and regions, certain specific points on this diagram are extremely significant. These are the invariant points.
Invariant. Meaning
Right.
things don't change there.
Sort of. It means 3 phases are in equilibrium simultaneously, but only at one specific fixed temperature and one specific fixed composition. You can't change either without losing that 3-phase equilibrium. The Fayette diagram has a couple of really important ones.
Okay.
First, there's the eutectic point. You find this higher up in temperature and carbon content, 4.308% carbon and 1147 degrees C.
Eutectic. What happens there?
The eutectic reaction happens upon cooling. The liquid phase, right at that specific composition and temperature, transforms directly into a mixture of 2 solid phases, austenite and cementite. It's described by equation 9.18 in the text.
Liquid becomes 2 solids at once.
Exactly. This reaction is particularly relevant for understanding cast irons, which usually have carbon contents up in this higher range, above 2%.
Okay, cast irons. But what about steels?
Well, for steels, here's where it gets really interesting. This is the eutectoid point. Eutectoid meaning eutectic-like, but occurring entirely in the solid state.
Okay.
It's located lower down. 0.76 weight percent carbon and a temperature of 727 degrees C or 1341 F. This is a crucial point.
Why crucial?
Because at this point, upon cooling, one solid phase, the austenite containing exactly 0.76 W2% carbon, completely transforms into 2 different solid phases. It transforms into the low carbon
alpha,
which can only hold 0.022 W2% C at this temp, and the high carbon cementite, which is 6.7 W2%. This is equation 9.19.
So solid austenite breaks down into solid ferrite plus solid cementite.
Exactly. And this eutectoid transformation is incredibly important because it's the fundamental basis for most heat treatments we apply to steels to control their properties. Manipulating this transformation is key.
So at 727 C, that austenite essentially decomposes into this mix of ferrite and cementite. And the specific structure that results from that transformation is key, isn't it?
Absolutely. The final microstructure, how those phases are arranged, is critical. And it depends mainly on the carbon content and, in the real world, the cooling rate. Callister's discussion here in section 9.19 focuses on the microstructures that develop under very slow cooling, basically equilibrium cooling as predicted by the diagram.
Okay, so slow cooling first.
Let's walk through how different compositions behave. Consider an alloy that has the exact eutectoid composition, 0.76 weight percent carbon. Let's follow path X in figure 9.26.
Path X.
We start hot up in the austenite phase field, point A. It's all uniform austenite grains. Then we cool it very slowly. As it cools down and hits exactly 727 C, the eutectoid temperature, point B.
The transformation happens.
Right. But the austenite doesn't just turn into, like, separate random blobs of ferrite and cementite. Instead, the entire volume of austenite transforms into a unique, layered microstructure. We call it pearlite.
Pearlite, layered. What does that look like?
Imagine alternating thin plates or sheets lamellae of the two phases, ferrite and cementite. If you look at pearlite under a microscope, like in the ferromicrograph in figure 9.27, you see these distinct stripes or layers.
Like a fingerprint pattern.
Yeah, kind of. The lighter, usually thicker stripes are the softer ferrite, and the darker, thinner stripes are the hard, brittle cementite. It gets the name pearlite because under lower magnification, the way light reflects off these fine layers can give it a shimmering, iridescent look, a bit like mother of pearl.
Ah, okay. Why layers, though?
It comes down to diffusion. Remember, you have austenite with 0.76% C transforming into ferrite with only 0.02 per 2 C, and cementite with a whopping 6.70% C.
Big difference in carbon concentration.
Huge difference. Carbon atoms have to move. They have to diffuse out of the regions becoming ferrite and into the regions becoming cementite. The layered structure, shown schematically in figure 9.28, is a very efficient way for this redistribution to happen because it minimizes the distance the carbon atoms need to travel. They just shuttle sideways between the growing lamellae.
Makes sense. Minimizes diffusion distance.
Exactly. And pearlite as a whole, as a microconstituent, has properties that are sort of intermediate, stronger, and harder than pure ferrite, but more ductile than pure cementite.
Okay, so an alloy with exactly 0.76% carbon becomes entirely pearlite upon slow cooling. What happens if the alloy has less carbon than that, say 0.4%?
Good question. Alloys with carbon between, say, 0.022% and the eutectoid 0.76% are called hypoeutectoid alloys, hypo meaning less than eutectoid. Let's follow Pathior in figure 9.29 for composition C, which is less than 0.76%.
Pathior.
Again, we start hot, all austenite, point C. As you cool down, before you even reach the eutectoid temperature of 727 C, you cross into a two-phase region on the diagram, the alpha plus austenite, points D and E.
Right, above the eutectoid line.
In this region, ferrite starts to form first, directly out of the austenite. This ferrite typically nucleates and grows along the boundaries of the original austenite grains. See the schematic at point D in figure 9.29.
Okay.
Because it forms before the eutectoid reaction happens, we call it proeutectoid ferrite. Pro meaning before.
Proeutectoid ferrite, got it.
Now, as this proeutectoid ferrite forms, remember it has very low carbon. It effectively rejects carbon into the surrounding remaining austenite. So the austenite that hasn't transformed yet becomes progressively richer in carbon. Its composition moves along that phase boundary line MO, towards the eutectoid composition of GREET 7.6% C as the temperature drops towards 727 C.
So the leftover austenite heads towards 0.76%.
Exactly. Then, right at 727 C, point F, all of that remaining austenite, which has now conveniently reached the eutectoid composition, transforms into
Pearlite,
just like we described before. The proeutectoid ferrite that formed earlier just sits there. It remains as part of the final structure.
So the final microstructure for a hypoeutectoid alloy, cooled slowly, is a mixture of that initial proeutectoid ferrite and colonies of pearlite, like in the micrograph figure 9.30.
Precisely.
If you look at it, you'd see maybe larger, lighter areas of the proeutectoid ferrite, often outlining the original austenite grain boundaries surrounding these darker, striped patches of pearlite. So you really have two distinct microconstituents, the proeutectoid ferrite and the pearlite.
Exactly right. And the source explains how we can figure out how much of each we have. Using the lever rule applied just above the eutectoid temperature on a specific tie line, shown conceptually in figure 9.3.
A lever rule, okay.
We can calculate the relative mass fractions. The tie line essentially spans from the ferrite composition, 0.022 per C, to the eutectoid composition, 1.76 per C. Equations 9.20 and 9.21 give the fractions of pearlite, WP, and proeutectoid ferrite. The book even works through example problem 9.4 for a 0.35 W2% C alloy,
Okay.
showing you get about 56% proeutectoid ferrite and 44% pearlite by mass. You can also use the lever rule across the entire region at a lower temperature to find the total fraction of each phase total ferrite, which includes ferrite within the pearlite, and total cementite. But often, thinking about the microconstituents is more intuitive for understanding properties.
Got it. Protectoid ferrite plus pearlite for hypoeutectoid steels. What about the other side? Alloys with more carbon than 0.76%, like maybe 1.0% C.
Right, those are the hypereutectoid alloys. Hyper meaning more than eutectoid. This covers the range from 0.76% up to about 2.14% carbon. Beyond 2.14% is generally the realm of cast irons. Let's follow path C's in figure 9.32 for composition C.
Okay, path C, C greater than 0.76%.
Start hot, all austenite again, point G. Now, as you cool down, you enter the two-phase region, point H, austenite plus cementite.
Ah, so cementite forms first here.
Exactly. Before you hit the eutectoid temperature, cementite starts to form directly from the austenite, again, often along the original austenite grain boundaries. See the schematic back at 2. Because it forms before the eutectoid reaction, we call this.
Protectoid cementite.
You got it, protectoid cementite. Now, as this high-carbon cementite, 6.7 per cc, precipitates out, it takes carbon out of the surrounding austenite, so the remaining austenite becomes progressively leaner in carbon. Its composition moves down along the phase boundary line, line PO, towards the eutectoid composition of 0.76 per 6c as the temperature drops to 727 C.
So the remaining austenite again heads towards 0.76% C, but from the high carbon side this time.
Precisely. And then, at 727 C.I, all of that remaining austenite, now at the eutectoid composition, does what?
Transforms into pearlites.
Transforms into pearlite, and the pearlite cementite that formed earlier just remains part of the final structure.
Okay, so for hypereutectoid alloys, slowly cooled, the final microstructure is a mixture of proeutectoid cementite and colonies of pearlite,
Yeah.
like in figure 9.33.
That's the one.
Looking at the micrograph, it might look superficially similar to the hypoeutectoid structure, but instead of those larger light areas being soft ferrite, you'd see networks or maybe thicker layers of the hard, often light-etching proeutectoid cementite surrounding the darker striped pearlite patches.
That's a very good description. The two microconstituents are proeutectoid cementite and pearlite. And again, the source shows how to use the lever rule, using figure 9.31 again, but applying it differently, to calculate the relative amounts.
Okay.
This time, the tie line for microconstituents spans from the eutectoid composition, 0.76 per 6c, to the cementite composition, 6.70 per c. Equations 9.22 and 9.23 let you calculate the fractions of pearlite, WP, and proeutectoid cementite, WSEs.
So the lever rule is really versatile for figuring out amounts.
Extremely useful. Now, it's worth mentioning Callister also briefly touches upon non-equilibrium cooling.
Ah, right. The real world isn't always slow cooling.
Not usually, no. What we've discussed assumes very slow cooling, allowing everything to reach equilibrium as per the diagram. But in practice, cooling rates are often much faster crunching in water or oil, for example.
What happens then?
Well, faster cooling doesn't give the atoms, especially carbon, enough time to diffuse and form those equilibrium structures like pearlite. This can cause the transformations, like the austenite decomposition, to occur at lower temperatures than 727 C, or it can even lead to the formation of entirely different non-equilibrium phases, like martensite, which isn't even shown on this equilibrium diagram.
Martensite, that sounds important.
It's extremely important. This is actually the crucial concept behind heat treatment. By controlling the cooling rates, we deliberately create these non-equilibrium structures to achieve specific, often much harder and stronger properties. That's a major topic for later, Chapter 10 in Callister.
Okay, so this equilibrium diagram is the baseline, but reality often deviates. And what about adding other stuff? You mentioned steels aren't just iron and carbon.
Right. That adds another layer of complexity. The source points out, and shows in figures 9.34 and 9.35, that adding other common alloying elements, things like chromium, nickel, manganese, vanadium, molybdenum, titanium, significantly changes this phase diagram.
That's so.
They can shift the positions of the phase boundaries. Critically, they can drastically change the temperature and the carbon content of the eutectoid point itself. Some elements raise the eutectoid temperature, others lower it. Some shift the eutectoid composition to lower carbon, others to higher carbon.
So the whole map warps, basically.
Pretty much. And these additions are made deliberately, of course, to tailor properties. Things like improving corrosion resistance, like in stainless steels with chromium, increasing hardenability, how easily you can form hard structures like martensite, improving strength at high temperatures, or modifying the response to heat treatment. This really expands the possibilities way beyond simple iron-carbon alloys. That's covered more in section 11.8.
Okay, so pulling all this together then, what does this deep dive into the
Fe3C
diagram really tell us about the materials that build our world?
Well, fundamentally, it shows us this predictable relationship between the amount of carbon you put in, the temperature you heat it to or cool it from, the specific types of phases that are stable ferrite, austenite, cementite, and critically, the final arrangement of those phases into microstructures, like pearlite and those protectoid phases we talked about.
And understanding that relationship is powerful, isn't it? Because it explains why just tiny changes in carbon content, maybe just a few tenths of a percent, or simply cooling an alloy through that crucial 727-degree eutectoid temperature can completely transform the internal structure of the material.
Absolutely. And that internal structure, the microstructure, is what dictates its macroscopic properties, how strong it is, how ductile, how hard, how tough.
So this knowledge is really the essential starting point. It explains, why a soft iron wire bends easily, while a medium carbon steel beam can support a bridge, and a high carbon steel razor blade can hold that incredibly sharp edge.
Exactly. They all start as iron and carbon, maybe with a few other things mixed in, but their final properties are defined by the phases and microstructures that are predicted by this diagram and then manipulated through processing, especially heat treatment.
Which brings up a really interesting question, I think. Given that controlling properties is so much about manipulating these microstructures, and that real-world processes involve faster cooling, non-equilibrium phases, and alloying elements that change the map, how do engineers actually use this equilibrium diagram as a starting point to design those complex heat treatments and alloy compositions that give us the incredible diversity of steels and cast irons we rely on every single day?
That's the bridge, isn't it? From the fundamental map to practical engineering, definitely a lot to think about the next time you look at a steel structure or pick up almost any metal tool.